Okay, so the goal of this lab is to calibrate the thermistor. What does that actually mean? So if you were to take a thermistor and use a tool to actually graph its resistance and compare it against an increasing temperature, then what you would see is something that looks roughly like this, where you have a graph with the resistance of the thermistor plotted on the y-axis and the temperature in degrees Celsius plotted on the x-axis, where 0 degrees is over here, and then we'll say like 100 degrees is over here, and then vice versa. You have 0 ohms down here, and we'll say like 10 kilo ohms up here. If you were to do that, then you would see a graph which looks something like this, which is a logarithmic graph where the where the resistance on the resistor has a logarithmic relationship with temperature. Now, what you've gone and done is with the circuit that we've made a voltage divider, which in turn translates the changing resistance into a changing voltage, where as the resistance of the resistor is increasing, in turn the voltage that would be dropped across the resistor is also increasing, which then leads to an inverse an inverse proportionality relationship, where the voltage that you would see on the resistor, measured in the red here, would be inversely proportional, roughly, or an inverse version, roughly, of the graph to the resistance here, where this red value here is the voltage across the resistor. Now, as a reminder, really quickly, just to exactly what that means when I say the voltage, when we made it the divider earlier, we had 3.3 volts coming in, going into a 10 kilo ohm resistor. Then we had it going into our thermistor, and then out to ground. So what we mean when we say a voltage drop over the resistor is that we are taking a reading here and to ground, and taking a reading here and to ground with a voltmeter, and we're reading a given voltage over on this voltage on this line. Except instead of using a voltmeter to do this, what we're actually doing is we're taking the analog 0 or analog 1 or analog whatever pin, it doesn't matter, on the Arduino, and also the ground on the Arduino. And the analog 0 pin on the Arduino is acting as our voltmeter. It's the same thing. So the Arduino is, in essence, measuring this red line here, or some version of this red line here. Okay, so why is that important? Well, if the Arduino is measuring the voltage, yeah, then that means that to an extent, we're measuring the y-axis. However, we also need to know what the x-axis is. We need to know what the actual temperature is to make any meaning out of what the voltage on the resistor is, or what the resistance of the thermistor is. It doesn't matter. We need to know that. We thankfully, though, if you have the circuit set up correctly, also have the LM35 on the Arduino circuit. The LM35 is an adequate temperature sensor. In this experiment, we're using the LM35 as our given as our good temperature. We can take that as the temperature that the room actually is, and we trust that value. So what that means in terms of calibrating this thermistor is that, let's say we don't know necessarily what the resistance of the resistor would be at a given temperature. So if it was 20 degrees, we wouldn't know if the resistance of the thermistor would be at a given temperature. So if it's 20 degrees, we don't know that the thermistor would be 100 ohms or 1,000 ohms or what the story is. We want to generate some kind of mathematical equation, which means that when which is an f of x is equal to y, where f is a function and x is the resistance. Well, not actually the resistance, the voltage technically, because we're actually measuring the voltage, we're not measuring the resistance. Voltage produced here is equal to a given temperature. So we want to know that based off a certain value of voltage, there is a given function f that we can apply to that number, which means that we can tell the temperature. Once we have this, we can consider the thermistor to be calibrated, because this means that we know based off of the thermistor's resistance what the temperature would be. So to go about doing that, it's actually very simple. If you have followed my previous video, you should have the Arduino doing something along the lines of serial printing out two numbers, or a multitude of numbers, but you should have one number which is representing your temperature in the serial monitor from the LM35. And you should have another number which is representing the resistance, or the voltage, doesn't really matter. We'll say voltage from the thermistor. Now, in my tutorial, I never actually specified, okay, how do we take the value that the Arduino is measuring and turn that into a voltage? Again, the exact same way the LM35 works. The Arduino is going to map both of these between 0 and 1023. Oh. In my tutorial, I believe I went over the maths of how you can convert this value into a number for degrees Celsius, how you can actually do the formula to convert that into degrees Celsius. Similarly, there is a way of converting this formula into a voltage, and then from there, there's a further way of converting that back into its constituent resistance. However, the thing is, if you graph this number against this number, the voltage against this number, or the resistance against this number, in each case, each of these will have a different f of x equals y. So we'll have like this will be f of x, I don't know, we'll call this g of x, and h of x. Where it's like, okay, the resistance, for instance, the resistance is going to have a different function which correlates to the temperature than the voltage would, which correlates to the temperature, than the number measured on the Arduino would, which correlates to temperature. But the thing you have to understand is that if you take this number here and convert it to voltage, you're just doing some like pretty basic maths. If you do this voltage, take this voltage here and convert it to resistance, you're doing some more complicated maths. You're doing the exact same maths if you convert these if you do essentially be doing the exact same maths on these functions. So you don't need to convert to voltage or resistance. You could just take this value and graph this value against the temperature, and then you would know what the temperature on the thermistor is based off of that value. The downside of that, by not doing the math for the resistance, is it means that if you were to then make a completely different circuit with different resistor values, you wouldn't be able to say the thermistor is calibrated anymore. You need to redo the experiment. But in this scenario, because we're just keeping the circuit as is, knowing these values is enough to be able to calibrate the thermistor. You don't need to go out of your way to go and do all the extra math if you don't want to. So that's a pretty good explanation of what's going on. If you didn't understand any of that, don't worry, because what you actually need to do is just this. If your Arduino is outputting the temperature, well, okay, we'll stick with blue. And I mean the temperature as in the maths that has been done to take the LM35's reading and convert it into degrees Celsius. And the Arduino is also at the same time outputting the thermistor value, where temperature is given in degrees Celsius and the thermistor's value is just some arbitrary value between 0 and 1023. Literally all you need to do is just take a table of points. Like, the Arduino will be serial printing these however many times a second you have up. So you'll have your points here. Oh, Y1, X1. You need to get these in a table, or record these manually or with your code, or however you want to do it. Record a number of these, maybe 10, maybe 30, maybe go all out and do like 1,000 of them. Go nuts. It doesn't matter. The more you take, the more accurate it will be. Get that, and then put it into Excel so that it is in a scatter XY chart where you have all of these points graphed like this in Excel. Like it's in a scatter XY chart in Excel. And then finally in Excel, go into the options and click add a trend line. Then specifically, you're going to want to add a logarithmic trend line. I'm tired. I don't know why I had to bother writing out that word. Anyway, logarithmic trend line, specifically because the relationship of a thermistor between its resistance and its temperature is a logarithmic one. The shape that these points should form, if you've done your experiment or your measurements correctly, should be a logarithmic line. So if you go and you add a logarithmic trend line, Excel should add something roughly like that, where it's forming a logarithmic shape that fits those points. If you go into the settings in Excel, I'm not bothered screen recording, but you can find it, and you can find tutorials on YouTube explaining how to do this as well. There should be an option specifically on the desktop app, not on the browser version, where you can make Excel display the exact equation of your resistor value. So, or sorry, the exact equation of this trend line. So it might be like minus 0.2 ln of x plus 0.034, like whatever. I'm just making up numbers, but it will display something like this. This value here, that is your f of x. Like that is the calibrated function for the thermistor. So now you have your f of x. If f of x is equal to, I'm simplifying it, we'll just say minus 0.1 ln of x, then it means that at any given value between 0 and 1023, if you took that value and put it into the function minus 0.1 ln of x, it would give you back the temperature, which is, that means that this function now has calibrated the thermistor. You can now use the thermistor on its own to have a rough confidence of what temperature it is. One of the things you'll need to do your lab report on is to what degree you're confident in this reading versus the reading that the LM35 gave. And so within this, it's up to you then to read the datasheet of the LM35. Literally Google Texas Instruments LM35 datasheet. You'll find it online. Same with every other component ever in existence. But yeah, you can find the datasheets online if you Google for them. And you can look at the accuracies of that. And you can look at the accuracies of maybe the thermistor or the accuracies of the Arduino. And you can comment about how accurate you think that your thermistor's calibration is in compared to the actual real world temperature. That is what calibrating the thermistor means. That is the goal of the experiment ultimately. That's like what you need to do or have done before Friday for the lab assessment. Now, the next thing is the actual lab assessment. What the lab guys are going to get you to do is they're going to get you to use a multimeter. You've all already been using these before, so I hopefully won't need to explain this too in depth, but pretty much there's a few things that you need to watch out for. Firstly, the multimeters that they have in the lab are set up where they'll have like voltage here. Oh, that's terrible. Voltage. And then like ohms, fucking like a weird diode symbol down here. I don't believe this is, I don't know if this is the exact layout. I'm just pulling this from memory. And then you'll have your amperage as well. So amperage like that and amperage like that. Okay. These, oh, that's not red. These wavy ones here are AC, which means alternating current. If you didn't do physics, it doesn't matter. AC is, this circuit that we're using is not AC. If you try and measure with these, you're not going to get any reading on the multimeter, and the lab guys are going to judge you, and you know, bad stuff. You just don't use these. Do not measure with these. If you're asked to measure the voltage, specifically measure the voltage with this, the V, where it has this symbol here, the two lines. This indicates direct current, DC. We're using a DC circuit, so you want to measure voltage in DC. Again, if you're asked to measure in current, you're going to be measuring with amps, which is in DC as well. Okay. Now, if you go ahead and actually look at a multimeter on the day, you'll see that the value looks a bit weird. So it'll be like the whole thing will be a dial, but specifically zooming in on that dial further, there'll be like we'll take the voltage as an example. You'll see something along the lines of it's like 220, 220K, 2M. This is all over the place. These numbers are kind of irrelevant. But what this actually means is it's indicating the scale of what the multimeter is reading. So if you have it on 2, then what the multimeter will do is this will be in volts. All of these units are in volts. Then this is in kilovolts, and then that's in megavolts. They don't put the V symbol for some reason. If there's no symbol, it just means it's volts. And then if there's a K, kilo, M, mega, same for all the other stuff. If there's this symbol, it means micro. Like they just put the symbol, but not the actual volts or amps on the multimeters for some reason. I guess they want to save on ink or something. If this happens here, it means that the multimeter is going to be measuring from 0 up to 2 volts. If the circuit is drawing higher than 2 volts, the multimeter will just output 1. And like an empty box like this, the screen will just be 1. Like it'll just say 1. And that pretty much means that the voltage it's reading is higher than 2 volts. It can't read any higher. It's just outputting 1. If it's like if it's less than 2 volts, like you're measuring 1.5 volts or something, you should see something along the lines of it's like this, where it's like 1.52 V. That's how you know it's working correctly. You can take that as your voltage. If you go up a stage, then now it's measuring between 0 to 20 volts. It will now be measuring specifically. It will tell you, okay, yeah, it'll measure. Okay, let's say you're measuring your 5 volt signal. It'll be like, it will tell you 5.1 V on the screen. Now, importantly, and this matters more so for current than it does volts. I kind of should have picked current instead of volts. If you go into the range here where it's like kV, it will not display it in, it will display it still like it's volts. So if you're measuring kilovolts, you're not measuring kilovolts, by the way. If there were kilovolts in the room, we'd all be wearing safety equipment, and if you touched it, you'd die. But semantics, I'm just as an example. If you're measuring kilovolts over your multimeter, the screen would display, like, let's say you're measuring 12 kilovolts. It would just display like 12.42. You need to understand that because you've chosen the kilovolt settings, that actually means 12,420 volts. So the lab guys are going to try and catch you out for that. Sorry, my handwriting is terrible. The lab guys may try and catch you out for that if you're measuring the current. Because what you might be doing is you might be measuring the current, let's say, in 20M, lowercase m. That means milliamps. So you're measuring in 20 milliamps. If you measure in 20 milliamps, again, equivalent of measuring in 20 volts or something, watch out, because it might, the multimeter might display something like this where it says 15. If you go and tell the lab guy, oh yeah, I'm measuring 15 amps, they're gonna be upset with, well, not upset with you, but I don't know, they'll mark you down or something, because you're not measuring 15 amps. You're measuring 0.015 amps. You're measuring 15 milliamps of current. So that's something important to watch out for. The other thing as well is measuring things like, oh yeah, how you actually measure things. If you're measuring the voltage of something, you measure across the component. I respect that some people don't know how circuit diagrams work, so I'm going to try my best and draw like an actual creative thing here that showcases the what it would actually look like in real life. But let's say you have like your resistor here like this. This is going to be awful. Let's say you have your resistor here like this, and it's got its silver legs coming out like that, and then you have like a red wire going off this way, and I don't know, a purple wire going off that way. Cool. And you've got your fancy stripes on your resistor. Yeah, great. If you have your multimeter red was not a good color because there's also a red wire. If you have your multimeter and you're measuring the voltage, the circuit diagram of what this picture would look like would literally just be this. It would just be a resistor like this. If you're measuring in voltage, the voltmeter goes across the component, which means you literally get your two legs of your multimeter. So you get your red multimeter probe, and you would just touch it off of the inside of this resistor leg here. So your multimeter probe will have like a little spike at the end of it. Touch it off the resistor leg here, and then correspondingly you'll have a ground multimeter probe. Touch that off of the resistor here, and that is the physical equivalent of this here is the physical same as doing this circuit diagram here. This is measuring across the resistor, or otherwise known as measuring in parallel. Now, if you were instead asked to measure the current would not be measured this way. The current is instead measured, one sec, get rid of this. The current is instead measured in series rather than in parallel. So what that means is your current would be measured by putting your ammeter here. Also, when I use the symbol A for ammeter and V for voltmeter, this is a circuit symbol for talking about like measuring the voltage and measuring the amperage in a circuit. In actuality, it is the same multimeter. It's not like they're different components. It's just when you're measuring in voltage, your multimeter's dial will be selected towards the voltage section. And then when you're measuring in current, you're going to change the dial so that the dial is measuring the appropriate current section. That's all that means in like actual physical, like using the multimeter terms. If you're using the multimeter like that though, then to measure the current in series. So you're going to go ahead and you're going to actually physically disconnect your power. And then from there, what you want to do is you want to get your multimeter. One sec. This software is buggy sometimes. You want to get your multimeter and you're going to measure with the red probe. You're going to measure here on the power line. So you're going to break the power from the circuit. The circuit will be completely broken, not plugged in. You're going to have your power wire loose one end, and then the like receiving end of what otherwise be the power wire on the other end. And you're going to actually physically connect the circuit together. You're going to complete the circuit across your multimeter. So your multimeter is going to be, all of the voltage from your circuit is going to go through your multimeter. So your power is going to be flowing, like your electricity from your power is going to go from the power line through your multimeter, out of your multimeter, and back into the rest of your circuit. So you're not measuring across, you're measuring in series. If you do this, your multimeter should be measuring the resistance, or sorry, not the resistance, your multimeter should be measuring the current drawn by the circuit accurately. It could be the case that you're asked to measure the current this way. Lastly, to measure the resistance, you're going to go and take your component while the circuit is unpowered, and the exact same as the multimeter, you're going to measure across the resistor. That should be adequate for measuring the resistance of a given component. You can't really do it while it's powered. It's ill-advised to measure the resistor while your circuit is powered. It's not going to really give you a meaningful result anyway. So yeah, make sure your circuit's unpowered when you're measuring the resistance of something. That's all. Okay, so to connect the screen to the Arduino, there we go. Okay, to connect the screen to the Arduino, it's actually not all that complicated. In the one of the engineering lab briefings, I guess we're about to find out which one. One second. Yeah, here. Um, there is example code for how you actually display the temperature to the LCD. So, okay, pretty much what you need to do is you can't just go ahead and what I've seen loads of people do is they just go, okay, grand, cool. They copy all of this directly into their code and they just paste it at the bottom and pray that that works. That's not how any of this works. So, um, the order and structure of your code actually matters in Python, or not. Sorry, I'm very tired. In Arduino, in this case specifically in I think Arduino is C++. Um, what this means is that the void setup, for instance, and then the loop down here actually mean that the Arduino is going to run whatever code you put in them at setup, and then whatever code you put in the loop is going to just loop over and over again. So you can imagine logically, it makes absolutely no reason why you would have a setup down here. Like the Arduino is gonna see this code and try and like your computer is gonna try and compile it, and and the computer is gonna go, wait, hang on, okay, so you're telling me to set up. Oh, I hit the wrong button. You're telling me to set up. You're telling me to do a setup function here, and then you're telling me to do a big loop and do my code, but also after an endless loop, I'm apparently meant to set up again, even though the loop that I'm about to do is endless. That makes no sense. What the heck? And it will give you an error and it won't compile. You need to instead see, okay, there's some example code here. Specifically, there's example code here that's inside of a setup function. There is a void setup function in their example code. You're going to need to go and take this example code here and put it inside your original setup function. So you might have, you know, you might have code already in your. I'd hope you have code already in your setup function. Otherwise, I have no idea how you've been doing the Arduino lab. You'll have code in here already. That's like the code that you've written to get the thermistor and the LM35 to work. You're going to want to copy. I'm using the red for the copied code. Copy the code into your setup function and just put it in the bottom of your setup function. That's just how it works. If you were to have another setup down here somewhere, that will result in an error because it makes no sense to have another setup. Firstly, why would you be setting up twice? And then secondly, how do you expect the setup to run if it's coming after an endless loop? Code will always execute in a logical, like, downward step order. So it will be one after the other over and over again. And in the case of a loop, whatever is inside of the loop will execute line by line. So 1, 2, 3, and then go back to the top. 1, 2, 3. 1, 2, 3. It will execute over and over and over again but specifically sequentially going down a line logically. So you're going to need to take the code that's in your setup function and copy it into the bottom of the setup function you already have. Same thing with the code in the loop. You're going to need to take the code in the loop and copy it into the bottom of the loop. Now, what people also don't realize is if you do this, the screen, and you put the screen in the right area, you've wired the screen in the right area. I'll tell you how to do that now in a sec. Then you should see the screen at the very least light up, but all it's going to do is show the same number, 22.34 over and over and over again. Why is that? Well, let's go and look at the code that the example code is written. They have float dtemp here, 22.34, and then down here they're doing matrix dot print dtemp, where dtemp is this value here. So it's printing 22.34. You don't have any dtemp in your code. Well, I mean, if you miraculously decided to call your temperature variable dtemp, then well done, this segment doesn't apply to you. But if you have, let's say in your code somewhere, you're doing like serial.print thermistor temperature or something like that, you'll have a variable that's called, we'll call it thermistor temperature. It gets stored down to therm temp. if you're doing serial.print, a serial.print, okay, just sp serial.print of therm temp tt. If that's in your code somewhere, where it's serial printing therm temp, if you want your screen, your matrix display to actually display the thermistor temp, then you need to do matrix dot print, and then you need to put whatever that variable is in here. So in our case, we would be putting therm temp in here. But if you called it like thermistor value, if you called it temperature reading, if you called it like any number of things, it doesn't matter what you actually called it. You need to put the exact same text, and it's case sensitive. You need to put the exact same text in matrix.print, because matrix.print is printing whatever value is in it. If you don't leave it, if you don't change it, you leave it as dtemp. If you don't do anything with dtemp is just going to always be 22.34 and never change. So the screen is just going to show 22.34 and never change. So you have to actually edit the variable in it specifically for your use case. The final thing now is you may be getting an error, something along the lines of it's like matrix function does not exist, or library not found, or something like that. When you actually try and run this code, you're going to run into an issue with potentially with these lines up here, which is these are the lines for the libraries that you're using. If you're using your own laptop, or alternatively, if you're just particularly unlucky with the lab computer that you've picked, the libraries might not be installed, and by default in any Arduino instance, they shouldn't be, because they're very specific libraries. This is a very quick cursory overview, just so you have an idea of what I'm doing, because I am very tired, but I also believe that anyone who's learning anything should have an understanding of what's going on behind it, rather than just rote learning, especially now that we're in college. But pretty much, if you purchase a screen, like let's say the Arduino screen, yeah, that screen has a corresponding bit of code that tells the screen how to work, how to turn on. The manufacturer who makes the screen does not expect you to magically know how to write that code and manually write every single individual bit. You could, but it would take forever, and if you were an engineer who was using a screen, every engineer all over the world would have to write their own version of the exact same code. It makes no sense. So what the manufacturer does is they write one bit of code, which they take as like the gold standard for like solid, well-written code, and they put it in this nice little package together called a library. That library can be added to the top of your code. And what that means is that when you're writing code, let's say a function like matrix.print, matrix.print is not normally a function in Arduino, but now that you have that library, it's included the manufacturer's code. The manufacturer has coded matrix.print to mean something, and so your computer, when you write matrix.print, will actually go, okay, matrix.print, that corresponds to this library here, and then it will go and it will find that file on your computer, because you'll download that file, it'll be somewhere, and it will go look at the code in that file, and it will go use the function in that code, and then it will go all the way back to your original Arduino code, and it will do the next line then after that. But it is a way pretty much of including or running other people's code within your own code. That's the point of a library. And so to get this screen to work, we're downloading the libraries from Adafruit. Adafruit are the people who manufacture this screen. To do that, we go to the Arduino IDE. I'm opening mine now. Also, you may see a different version of this IDE, depending on what you're using in the lab. That's because there are that's because there's different versions of the Arduino IDE depending on like what version you've downloaded. The one in the lab is quite old. What I'm going to do here with this new one is I'm going to hit this button here, which is the library manager, and then specifically the libraries that are in the code. So we have sbi.h, wire.h, Adafruit, gfx.h. Let's just go for all of those. Let's Google for SPI, search. I should have all of these already. Yeah, nothing's coming up for SPI. Wire, nothing comes up for wire because I already have that. The one that you actually need to search for, the one that you need to install, is Adafruit _ GFX. Now, see the way mine says update? It's because I already have it installed. I have everything here ready to go. I have the Adafruit GFX library all ready to go, which means that if I put these lines of code here in my actual code, if I put all of this in the top of my code, and I compiled it, it should compile just fine, no errors whatsoever. The first compile always takes forever, but you know, it doesn't matter. You have an understanding of what I'm doing. Yeah, just fine. And then if I were to remove this library and I try and compile again, it should completely fail. Or if it doesn't, then yeah, there you go. Compilation term, no such file or directory. It can't find it. So that's what you need to install the files for, because it needs to actually look for the file that you're including, the library that you're adding per se. Okay, then the last thing that you need to do, I don't know if they have it in the lab report here, is the LCD screen. You should be pretty much able with your LCD screen to wire it the way it is set up in this lab here. So I'm not going to go into it too much, but like there's literally just a section on the side of the Arduino where miraculously A5 through A2 all line up perfectly. So it should be as simple as taking like your screen looks something like this, where you have like a green board here, and then your blue screen is actually on top of it. There should be 4 little pins on the side of the screen here. Well, 8 technically, 1 on either side. They should just slot in perfectly to the Arduino on this side, and you could just theoretically put it straight in A2 through to A5 and then run their test code, and it should all work. I'm not going to go into the wiring beyond that because I'm tired. I want to go to bed. If you don't have one of those, you need to manually wire it yourself. I'm not going to go into it, but if you want to go into it specifically, then go to Adafruit. And then I already had it set up here, but you're going to search 7-segment display. Specifically 0.56 inches. Oh. Yeah, cool. That looks roughly like what we're using. Oh wait, no, not that one. That one doesn't have a circuit board underneath. Where's one that does? You have a circuit board underneath. Yeah, cool. That looks similar enough to what we're using. And then, oh yeah, down here you go to learn, backpacks, and then go over here. You have overview of every type of screen they make. We'll go to the 7-segment display one. And then assembly and wiring. Cool. There you go. And you can open this image in a new tab, and you can see exactly how they have it wired. And you can just copy this wiring as well. That's another way of doing it. If for whatever reason your screen is missing the fancy green circuit board that lets you line up all the pins perfectly without needing to think about it. If that's not there, if where's my app? If the screen doesn't have like a green board like this, and then the actual screen itself like this, if this bit here isn't there, then you're gonna have to wire it yourself. But as far as I can tell, they're on all of the screens, so it doesn't matter. Yeah, anyway, that should be all you need to wire the screen.